Our geopolymer session was a special event fostered by Professor Nicola Babini himself, who asked me to really, with pressure, to participate to this ICC2, and we have done it with pleasure. I will not repeat what is in the roadmap. You have it in printed or on CD. I will provide you with some of the conclusions that are important. And in fact, this is a new area of research which involves chemistry, which is new for the majority of you. And we have topics that are crucial for the development of this technology, which can be used in a very wide variety of applications, starting from low-tech, low-cost to high-tech, high-cost. From the 14 research themes that have to be now pursued, starting from now, I've only selected a few that I will just briefly talk about. For example, we have to continue to demonstrate the polymeric character of geopolymers. We have discovered the geopolymeric micelle under the electron microscope of 5 nanometers particulates that correspond to well-defined polymers, and we can determine the molecular weight and the dimensions, and we have to improve the physical tools in order to get real data on what we are synthesizing. Number 2, we have to redefine and reinvent properly an ancient technology, which is the technology of making water glass. Water glass is one of our major ingredients in producing geopolymer. And in fact, what we have from the industry, what we have in terms of quality controls, in terms of homogeneity of materials, in terms of structures, is no longer adapted to what we require. And we have to better understand the molecular structure and try to modify and master the manufacture process and invent new systems and new quality control, because we need quality control molecular size. Like you are needing nano, we need molecules to be really perfect, and we have to know what type of molecules we are dealing with. We have seen that the results of the reaction between metakaolin, we get what we call a solid solution. It is a mixture of well-defined geopolymers with different SiAl ratio, and so far nuclear magnetic resonance spectroscopy is unable to separate between the 2 or the 3 or the 4 that are constituting this solid solution. The only way is to heat up the material and to wait until they crystallize, and then we get nepheline type framework, calcite type framework, lysitic type framework, and so forth. So we have to develop and invent a new way of detecting these phases more precisely. We have to continue our research in including phosphate units into the siloxo, the siloxo sequences, because it provides new properties. Essentially, since it is an alkaline-based system, we have to switch to the acidic-based system in order to be capable of using our resins as matrix for fiberglass, for example. So far, when we are doing composite, which includes geopolymeric matrix, we are only using carbon fibers or silicon fibers. And this is with this material that we are producing and making advanced composite material. And then we have to take advantage of the fact that we are sister of silicones, organic mineral geopolymer, and take advantage of this compatibility. The organic silicones are sensitized in 2 alkaline-based medium or acidic-based medium, and we will have different ways of manufacturing hybrids, and this open big potential for us. Then we are strongly involved in the use of this geopolymer chemistry in ceramic processing, and it is to introduce and develop the low temperature geopolymeric setting. An example is the production of low-cost building materials in developing countries, and this is one of the basic programs for the ceramic and brotherhood in Africa that we are presently discussing. One of the major results, we had several posters, but one which is really striking is the following one. Low energy, low CO2 technology for the ceramic industry. If you look at the energy consumed to make a tile with the geopolymer chemistry, you divide the energy by 5 or 6. If you realize the production time with a ceramic tile using geopolymer chemistry, you divide this time by 12 or by 6. For low energy, low CO2 technology for cement and concrete, if one is allowed to emit 1 ton of CO2, Portland cement will produce 1 ton of Portland cement, but with geopolymer cement we get a reduction of CO2 by 90%. If we look at the energy content, the megajoule per 1 ton, Portland needs more than 3,000 megajoule, and geopolymer, depending on which type, rock-based geopolymer or fly ash-based geopolymer, well, you divide by 5 or by 6. And then we can make bricks. Bricks not at 700, not at 800, not at 1000 degrees C, but at 70 degrees C. Totally different. This is chemistry. It is not the fire ring of the elements. And this is our program for ceramic brotherhood, and that will be fostered now. And in fact, one of the biggest discoveries is to take this knowledge and try to understand what happened in the past, and happened with archaeology, happened with archaeological ceramics, because we are astonished to see what our ancestors were capable to make. And this one, we discovered, we know that we have the oldest ceramic made by mankind. This is the Venice of Don Vestornici in the Czech Republic, 25,000 years old. Usually, ceramic have been invented during the Neolithic, 15,000 years later. But here we have a ceramic. How have they done it? Well, very easy. We have replicated it, dried at 80 degrees C, put it in a garden fire in a reduced atmosphere, 300 and 400 degrees C, and we got our Venice. This is how it has been done, provided the chemistry is in place, and the chemistry is very easy to achieve with ashes, with clays, with salts that are commonly found in clays, and so forth. You find other information in the book Geopolymer. Thank you very much for your attention.